Yes, ferromagnetism. Conceptually, ferromagnetism is similar to the paramagnetisms, but here we have the small difference between ferromagnetisms and paramagnetisms. So, in paramagnetisms, the magnetic moment of many atoms tends to align in the small region, that is, the small domain is there, whereas in the magnetisms, no magnetic moments are randomly arranged until the external B align them. So when the B be removed, they are not aligned. Since domain are very small and hence randomly oriented. So there is no domain in the paramagnetics. Here M and H do not have a simple linear relationship. Here in the paramagnetisms, M is directly proportional to H. Here for the magnetic susceptibility is equal to M upon H. That is linear in relation. So non-linearity of ferromagnetic material has to be explained. This has been tried by the BH curve, that is known as the hysteresis curve. In the hysteresis curve, we plot the graph between B and H. Here we see that from F to B point, we are increasing the magnetic field H to H naught, and then again decreasing the magnetic field, we reach at point small c. Here H is 0, but C is again there, and that is known as, so AC is called retentivity. And we then move to the reverse the sign, that is flip the magnetic field, applied magnetic field. Again we got the point E. Here is the saturation again, and from E again we changes the sign of the magnetic, again we reduce the magnetic field, then we get the this F E to F curve. So here I have written, that is here we apply the external magnetic field of x-axis and measure the B along y-axis in paramagnetic material. Starting the value of H, then decrease it to 0, then flip the directions to minus H0. What will happen, we will see. When H is equal to 0, V is non-zero. This is called the retentivity, that is the residual magnetism is there. When B is 0, H is non-zero, then H is called the corrosivity. And point B and E shows the saturations of B. Point B and C is called the saturation. Point C and F are a permanent magnet, and because when H is equal to 0, that is field switch off, there will be a sum returns to the randomly oriented domains. What and not all, hence object is permanent magnets. Now we want to calculate the energy loss. Consider a small thickness dB on the hysteresis law. For any value of current I, the corresponding flux phi is equal to V into A. So we find the change in flux, that is dB into A. Then work dW is given by the ampere into turns into the change of flux. So N is the number of turns, I is the current, then d phi is the change in flux, and so dW can be calculated. Here A into L is the volume, so H dB. Integrating W, we get the V into H dB. Work done per unit volume is equal to the area of the hysteresis loops. So we can find the power here. If F is the frequency of the each cycle, then the power loss in the hysteresis curve can be calculated as the F into the volume into the area of the loop. So next is the Langevin theory of diamagnetisms. From Langevin theory of diamagnetisms is that he explained the how to calculate the magnetic susceptibility of the diamagnetic materials. He assumes that the magnetic dipole moment is given by the M is equal to I into A. And then he calculates the magnetic dipole moment. But we know that the magnetic flux phi is equal to V into A, that is B is equal to pi r square. Now Faraday's law, epsilon is equal to d phi upon dt, that is pi r square dV upon dt. Here EMF is equal to 2 pi r e. E is the electric field here, minus pi r square dB. Then we calculated the E. From E we calculate the multiply with charge E. Then we get the force, and from it we calculate the force is equal to the mass into accelerations, that is rate of change of velocity we calculate. Then upon cancellations we calculate the value of the dV, that is dV is equal to minus er upon 2me mu dh into 2e. From this dV is equal to 2 dm upon dr, that is the change in magnetic dipole moment. Dm is equal to er upon 2 into dV, that is minus er square upon 4m into dh. Here we have assumed that the electron are revolving in the circular orbit, but actually the circle is not exactly circular. So motion is not exactly circular. So we take the average value of r. Therefore dm is equal to minus mu naught e square upon 4 in times of mass into o square into dh. From here we get the magnetic susceptibility is calculated here in the term of average value of r square. So r square is again calculated for xy plane, that found to be 2 by 3 r square. So we put the value here, the value of 2 by 3 into capital R square, where capital R is the average value of the atomic radii and radii of the electron revolving around the nucleus. So we calculate chi diamagnetic is equal to minus mu naught nz e square upon r square upon c. What conclusion we have drawn is that is the diamagnetic material is susceptibility of diamagnetic material is directly proportional to the number of the electrons. Number two, the susceptibility of diamagnetic material is independent of the temperature, because the temperature is not seen here, so it is independent of the temperatures. So this is the method to calculate exactly the diamagnetic materials. Thank you.